Welcome back, students. So this is the part 2 video of our unit 2 revision. In this particular video we will be dealing with the remaining topics. The first one is MOSFET and the second topic we will be dealing with is the op-amp. Now what is the MOSFET? It is again one kind of a transistor, as I said already in the earlier video. As far as the transistor is concerned, it can be BJT, bipolar junction transistor, or it can be MOSFET, which is a metal oxide semiconductor field effect transistor. Now what is the difference between MOSFET and the BJT? BJT is a current control device, while as MOSFET is a voltage control device. As we have seen in certain numericals as well, if we look at the BJT, it was governed by equations like IC is equal to beta IB, or equation like IC is equal to alpha IE. So the output parameters here was current and the input parameters also were current only. So it is a current control device. While as if we look at the MOSFET, it is governed by let us suppose if we talk about the JFET, we have a equation that is called as Shockley equation, and that equation is given as ID equal to IDSS 1 minus VGS upon VP whole square. So if you see in this equation, what is happening that we have a control parameter VGS. So with the application of this VGS, we can control the amount of drain current. So in this way we say it is a voltage control device, and we will see this in the operation also, that if you want to control the working of the MOSFET, then VGS is the very important voltage. Now coming to the types, what are the different types of the MOSFET? So we have two main category of MOSFETs. One is called as E-MOSFET and the other one is called as D-MOSFET, enhancement and depletion. Now what is the difference between them? In an enhancement mode, the channel is absent. We have to apply the VGS voltage and we have to create the channel. While as in the case of a depletion MOSFET, the channel is already available. So you need to apply the voltage in the negative way so that you can turn this device off. So that's why this device, depletion mode, is called as switch on device, or you can say normally on devices, and enhancement mode is called as normally off devices, because we have to create the channel by ourselves. So again we will be once we will be dealing with the working, these things will be more and more clear. Now talking about the different terminals that we have in the MOSFET, like we said in the BJT, BJT was a 3-terminal device which was emitter, base and collector. Now if we look at the MOSFET, MOSFET is a 4-terminal device, and what are the names of them? We have drain, we have source, we have gate and the body. So if you remember last time I told you there was one analogy, that water analogy was given. So we had one knob over here, that knob we called as base, right? Now the water that was coming from here, so this particular thing we called as emitter, and this bucket which was collecting the water, that we called as collector. Now the function here is also same, but the names are different. This base is now replaced with gate. So the gate will also be like a control element only, which can control the amount of electrons that are moving from emitter to collector. Okay, but in this case emitter is called source, while as collector is called as drain. Now their definitions are again same. Gate is the one that will control how many electrons are moving from source to drain. What is source? It will be the source of all the electrons that are coming if it is a majority device as N. Then what is drain? Drain is an area where all the electrons will be collected, right? So this way we have 3 main terminals, and then we have 4th terminal also, that is called as body or substrate. So what is body or substrate? As you can see in the diagram here, it is a terminal that has been shown at this particular point in the figure. Now coming to the symbols, how do you represent MOSFET? If you see, there are 2 different diagrams shown for N channel and P channel. First of all, you should identify how we can identify the enhancement and the depletion. So if you can see the first diagram, there we have the second line is dotted. It is like this way. So in this dotted way, this indicates enhancement, And if the line is complete like this, as you can see here, the line is complete, and here you can see that line is dotted. So complete line means depletion, and incomplete line means enhancement. So in this way we can say this is enhancement and this is depletion. Then second thing is that if you see the enhancement mode, how to identify whether it is N type or P type. So that will be decided by the arrows we are having here. So if the arrow is moving inwards, it is N channel, and if the arrow is moving outwards, then it is P channel, which is the opposite of what we had covered in the BJT. In the BJT it was opposite, right? If suppose we had a transistor like this and the arrow is outwards, then it was NPN, and if the arrow was going inwards, it was PNP. But what is the case here? It is the reverse. If the arrow is outwards, it is P channel. If the arrow is inwards, it is N channel. But there is one more thing that needs to be taken care of, that what if the different symbol for the MOSFET is shown. Suppose if you see, this is also a MOSFET symbol, right? We have here only 3 terminals shown, which is gate, drain and the source. Now this kind of MOSFET is again because the arrow is on the source right now, so it will be N channel. So it is opposite of what is being represented here. So what we need to understand is that in the diagrams which are shown here, the arrow here is on the substrate also, okay, while as here we are having only source. Here you can see there are 2 terminals which are shorted. What are these 2 terminals? One is the source, another one is the substrate, which is represented with SS. And if we are having in a diagram only the source available, then the arrow moving outwards is N channel and the arrow moving inwards will be the P channel type MOSFET. So I hope this is clear, like how will you identify first of all enhancement and a depletion, and second thing how to identify whether it is N channel or P channel. So we have one simple question: which of the following terminals does not belong to the MOSFET? So I said MOSFET has drain, gate and source. So base is not the correct one. So base is the right option here. So let us understand the constructional details of N channel E-MOSFET. So we will be studying the enhancement MOSFET and it should be N channel. Now when we say that it should be N channel, then in this figure, first of all we talk about the substrate. Substrate is the building block, or you can say the base on which all the materials will be built. So this substrate should be of the material that is opposite of whatever is the channel type, So because our channel is N channel, so my substrate will be opposite, that is P type. So you can see here it is written, it is a P substrate, it is a P type substrate available there. Now the second thing is that we are having a doping of N type done for source and the drain, and that you can see here and here. The important point here is, as far as the amount of doping is concerned, we are having equal doping. Of source and drain. This is unlike the BJT, because in BJT we said that emitter is highly doped compared to the collector, but in the case of MOSFET we have equal amount of doping. So that makes one more point important, that source and the drain terminals are interchangeable. So suppose in this diagram we have source here and drain here, but we can interchange them also by saying that this is drain and this is source. That can also be done. So that is the second point. Then the third point is that, as we said, we will be studying the E-MOSFET. E stands for enhancement, and I told you in the definition also, enhancement MOSFETs are those MOSFETs where channel is absent, Now if we look at the diagram, we are having N here, means we are having electrons here, we are having electrons here also at the source and the drain, but in between we are having this path, this is called as channel, and this channel is not available. And this will be more clear once you will see the depletion MOSFET. In the depletion MOSFET, what you will observe, you will be having N channel here, we will be having N doping here for source and drain, and in between also we will be having one channel of N. So that is a depletion. But here we are having no channel, so it is called as E-MOSFET, enhancement mode. Then what are we having? If we look at the metal contacts, to make contacts, we are having these metal contacts of drain and source. Then the third terminal is gate. So before we are connecting the gate, we are having again one layer here. This is the layer of SiO2. The layer of SiO2 has in place so that we can have very high input impedance of MOSFET, and with the help of SiO2 we can also increase the breakdown voltage of this particular device. Now coming to the operation of the E-MOSFET, we have to first of all understand how to create a channel, because that is the very important part to understand the operation. For that, what we do, we are going to provide a voltage VGS. Now this VGS voltage will be provided between the gate terminal and the source terminal available here. Now what we do is we provide a voltage around gate and source. Let us provide a voltage like this, and it is a positive VGS. Positive VGS means gate will be connected with the positive terminal of the battery. Now with this positive terminal of the battery that we connect over here, what is going to happen? We have to first of all realize we are having here p-type substrate. P-type substrate means, as we read already in the first video, that they are having holes as the majority. They are having holes as the majority, and there are few electrons also available as the minority charge carriers. Now the question is, once the voltage has been applied, because we are having positive terminal connected here, so it is going to attract the negative charge carriers, right? Because it will it will attract the opposite polarity. In that case, what will happen? If we see, first of all, we had here holes only, right? And since we are applying the positive voltage, so what will happen? These holes will try to move downwards because they will be repelled by the positive charge carriers, and as a result, what will happen? These electrons will try to shift here. Why these electrons will be trying to shift upwards? Because you are applying a positive voltage, and as you gradually go on increasing the VGS, you will see that more and more electrons will be attracted towards the channel, So what we will see is that once we will be crossing the threshold voltage, sufficient amount of electrons would be placed over here in between the source and the drain. Now that you can see in this diagram, also in the second diagram, as you can see now, once we have sufficient number of electrons, a channel will be created. So initially the channel was absent. Now we have created the channel, and that has been made possible by applying the positive VGS voltage. Now the question is, will there be any current? If suppose you are applying only the VGS voltage, shall we have any current? The answer is no. Now why is it so? It is because you need to apply one more voltage, that is VDS, so that we can drag the electrons from the source to the drain. Now that VDS voltage has been shown here. So with this positive VDS voltage that we are applying, we are having now here positive terminal, right? So this positive terminal of the battery is going to attract electrons. So it is going to attract the electrons. So as a result, what will happen? There will be a movement of electrons from this source position to the drain position. So in this way, what we will see, that the drain current will start increasing. Right? And in this diagram, what are we further showing is that the fourth terminal, that is called as substrate or body, it has been grounded. Then there is one more important point here. Since the substrate has been grounded, what if we apply here certain voltage? Let that voltage be like a negative voltage like this. So if we are providing here some voltage which is negative VGS, so in that case, what is going to happen? Because this P substrate was having electrons as the minority, and we are applying the negative voltage over here, so it is going to repel these electrons further. So this will help us in creating a channel very early. It means the effect of this V substrate as well as VGS will be applicable in that case, and we will be having a quick formation of channel in this particular case. Then we have to also define what is a threshold voltage, VTH. Okay, threshold voltage. Like we read in the diodes, there is a knee voltage which is around 0.7 volt for a silicon. In the same way, what is the minimum amount of voltage that we need in order to turn the MOSFET on? That voltage will be a threshold voltage. So it is what? It is the minimum amount of VGS voltage required to turn on the MOSFET. Now let us answer this question, why this MOSFET is called as enhancement MOSFET. The answer is because initially there is no channel. The channel does not exist when VGS is equal to 0, and once VGS is increased to certain value, let us suppose it is equal to VTH value or anything more than that. So in that case, what is happening? The channel that was non-existent, we have enhanced the creation of channel. We have enhanced what? Creation of channel, and that has been made possible with the help of VGS. So that is why the word enhancement MOSFET is being used. Depletion MOSFET, since it is not part of our syllabus, so we will not be covering that in this particular video. Now let us start the second topic, operational amplifiers. Now what are operational amplifiers? They are nothing but the multi-stage amplifiers. It means there are multiple stages of amplifier that are connected in cascade, and overall effect is that the gain is increased to a very large quantity. So it means the operational amplifiers are having a very high gain because of the multi-stage amplifiers. Because there's a concept in the analog electronics that if suppose every stage is having a gain of 10, if every stage is having gain of 10, so what will be the overall gain of this particular circuit? You have to just multiply all the values. So it means this can offer a gain of 1000 times. So that is what is exactly happening in the multi-stage amplifiers that are present in the operational amplifiers. So there are a lot of advantages that operational amplifiers do possess, and normally this IC is available to us, this operational amplifier is available to us in the form of an IC, monolithic IC that you can see here. Like this IC is the 741 IC, which is of 8 pins, and we shall see very soon what are all these 8 pins. So the definition also tells that operational amplifier amplifies the difference between the two signals and diminishes the common signal. So it has two properties. First one is that it amplifies the difference between two signals. As you can see, pin number 2 and pin number 3 is where you can give the input. The first one is called as inverting input, second one is called as non-inverting input, and we will see all these terms one by one. Then we have two voltages, one is the plus VCC, one is the minus VCC that we can apply. Then we have one pin for the output as well. Now you can see these are the 8 pins that are available in 741 IC. We have 2 pins for input, inverting and non-inverting. We have one pin for the output. Then to provide plus VCC and minus VCC, we are having these two particular pins. And then we have one pin number 8 which is not connected. Not connected means this pin is not used. Then the question is, what is the purpose of this pin? It is just to maintain the symmetry of an IC so that we can properly connect it somewhere, and we can do soldering also. And then we are having 2 pins for input offset. Now these pins might be used when suppose there are some errors in the MOSFET, there are some errors in the op-amp. It means that without providing suppose any voltage, if you are getting some kind of output voltage or output current, so in order to balance out that, we can use the input offsets in that particular case. Now let us understand what is inverting and non-inverting input. Inverting input means if suppose you are applying your input at this particular terminal, that is inverting terminal, then your output will be like this. So it means your output will be amplified, of course, because it is an amplified op-amp, and it is 180 degree out of phase. Okay, so that is what it means if it is an inverting. Similarly, what is non-inverting? Non-inverting means if suppose you are giving your input to the non-inverting terminal, then your output will be only amplified. but it will be in phase. So that is why the word non-inverting and inverting is being used. Okay, so that is what we have already studied. It's time to solve some questions. What is IC741? It is an 8-pin op-amp. What is the purpose of offset pins? It is to nullify the offset voltage. Now this is an important topic. What are the ideal characteristics of an op-amp? Now first we will read out all of them, then we will understand the reasons of the values as well. Now see students, the question here is ideal. So when we are considering the ideal values, so mostly the values in this particular table will be either 0 or infinite. But practically the values will not be 0 or infinite. There will be certain typical values that we can understand in terms of certain range. Now what is the first property of an op-amp? Its input impedance is infinite and output impedance is 0. Third one, its amplification, what we call as a differential gain, is again infinite. Common mode gain is 0, infinite bandwidth. V out is 0 when V in is 0, it means no offset, then infinite CMRR and infinite slew rate. Now we will try to understand the reasons behind the values that we are proposing over here. Now if we look at the first 2 points, that the input impedance must be infinity and the output impedance must be 0. Why is it so? It is because if suppose we are providing certain voltage, and that voltage we are providing like this. This is op-amp here, this is op-amp here. We are having here 10 volt and we are having here suppose 5 ohm, and this is also 5 ohm. Now what will happen? If suppose you see here, what is the voltage reaching this particular op-amp? It will be only 5 volt, right? Because we are having 2 resistors in series, so current will be same and voltage will be divided equally. So only 5 volt will reach the op-amp. But ideally what we will want, whenever we are providing the input voltage, that voltage should appear across the op-amp. Okay, like I will give one more example. Suppose we are having a voltage of 10 volt again. So this voltage, this resistance is suppose 1 ohm now, and this particular resistance, which is op-amp resistance, is suppose 99 or maybe more than that. It means the value is being increased for the op-amp. In this case, if you will again find out, the voltage will be around 9.99 volt across the op-amp only. So what have we understood from this example? It means if suppose we are increasing the value of op-amp resistance, then what is happening with that? Whatever is the input voltage you will apply, the maximum of that voltage will appear across the op-amp only. That is the reason why the input impedance must be very, very high. And this is what we say, ideally the value must be infinite. Because if the value is infinity, now see the third case, what will happen? Suppose we have a 10 volt, we have a resistance here of suppose 5 ohm or 1 ohm, and resistance here is infinity. Infinity means open circuit. For that you can refer to the revision of unit 1. Whenever there is an open circuit, then it means infinity resistance. Now if I ask you what is the voltage at these 2 terminals, so this voltage is nothing but it is equal to V in voltage, exactly. Because there is no current in the circuit, there is no drop, so Vx and Vin are same. So that is why Zin must be infinity. Now the second point is, why is it that the output impedance should be 0? Again, for that the reason is, once we get the output, suppose we get certain output, alright. Now this output we have to divide in 2 parts. The first part is the resistance here of an op-amp, and second one is the load resistor RL. Now what would we want? It is again same point. We would want that whatever is the voltage coming here, that voltage should appear, that current should appear across the RL only. So there should not be any drop over here, right? Again the same example, if suppose the voltage here is 10 volt, this is 5 and 5, So how much voltage will reach the output? Only 5 volt, because the rest will be a drop over here. So what are then we saying? If we want to have the output voltage of this point same as this point, then the resistance of an op-amp must be 0. 0 means short circuit. So once we will short it, so what will happen in the diagram? The resistance of an op-amp is short, and then we have the output resistance R out. So what will happen? Whatever is the current here, same current will flow here, and the same voltage will appear here. So that is why the output impedance must be 0. The third case is that amplification is what? Infinity. And that also we shall see very soon, that what is the reason and how mathematically it is true. Then common mode gain is 0. This is what we have read in the definition also. If I will show you the definition again, the first property is it amplifies the difference between the two signals, and second one is it diminishes the common signal. So ideal value then should be 0. And its best application we can see is in the form of a noise signal. Okay, suppose we have an op-amp. Alright, in op-amp we are giving V1 and V2 as two signals, and both of them are having certain noise available. So once we said that it will amplify the difference between the two signals, so what will be the output? You had to just do, like the formula is V0 is equal to A times V1 minus V2. So in an op-amp what we can write? V out is equal to A times, what is our V1? V1 is V1 plus N. What is our V2? It is V2 plus N. So you can see, students, V0 will be A times what? Noise and noise, it will cancel, it will be V1 minus V2. So the question is, what is happening to the noise? Because the noise is common to both the terminals, so they will cancel the effect of each other, and at the output we are watching that there is a signal which is not having any kind of noise. So the noise has been rejected. Okay, that is what we shall see in the CMRR also, this common mode rejection ratio. So how much we are rejecting this noise, that is also one important parameter. So the point is that the common mode gain will be 0. Then we have infinite bandwidth. Infinite bandwidth means if we look at the op-amp, we can use it for any range of frequency of operation. Means if we can use it for 0 Hertz also, we can use it for as high as a certain gigahertz also. Then we are saying that if it is an ideal op-amp, then V out must be 0 when no inputs are given. That is what should happen normally, right? If there is no input, there should be no output. But practically what we will see that because of the very high gain, sometimes it may happen that without any input you do get certain kind of output also. Then two important parameters are CMRR and the slew rate. Let us explain them also. Now what is CMRR? Like I told you, it is a common mode rejection ratio. So first of all, in this diagram what you are watching, the two terminals have been connected together and we have given one common signal. So it is a common mode. So in this case, what is the rejection ratio? That will be equal to 0 only, because both the values are same. So once we will take the difference of two, they will be same values being subtracted. So the value has to be 0 only. Now for CMRR, we have certain formula also, like CMRR is given by AD over AC, where AD is the differential mode gain and AC is the common mode gain. And sometimes this value will be very high value, so we can also represent this in logarithmic thing. We can write it as 20 log AD over AC with the unit as decibels also. So here will be the units dB. The last thing is the slew rate. Slew rate is again one important parameter that tells actually how quickly your op-amp is responding when you are providing any kind of voltage. So that is written here also. The slew rate of an op-amp is the rate of change in the output voltage caused by step change on the input. So if we are providing an input and we are changing the input, suppose in this particular figure, what are we doing? Input is changing from 0 to 1 here, or in this case input is changing from 1 to 0, and this is happening instantly. Then how much time will the output take to respond to these changes. So you can see here output cannot respond instantaneously, as it is very logical, because we have logic gates there, we have the transistors over there, so they will have certain delays. Due to that, what is happening, as you can see in the second diagram, when we are moving from 0 to 1, it is going bit slowly, it is taking some time, there is a delay of this much path. Similarly, when it is moving from 1 to 0, your input, it is happening abruptly here at the top, but at the bottom for the output you can see to reach from 1 to 0 there is a delay of certain time, right? So this delay is basically defined in terms of the slew rate. So it is measured as a voltage change in a given time with units as volt per microsecond or volt per millisecond. So the slew rate should be as high as possible to ensure that the maximum undistorted output signal is available, right? And how is it given? It is given as 2 pi f into V, where f is the frequency and the V is the amplitude. Now we understood as far as the ideal values are concerned. We said input impedance is infinity, but practically the value has been seen, it should be around 10 to the power 6, or if you are using BJT, and it should be around 10 to the power 12 also if it is FET. Then we said that the output resistance must be 0 ideally, but practically it is around 100 to 1000 ohm. Then the third point is input current is 0 because of the infinite resistance. When R is around infinity, then obviously the current will be almost 0. So ideally 0, but practically there will be some value which ranges from 10 to the power minus 12 to 10 to the power minus 8. Then the gain, I told you differential gain is ideally infinity, but practically it can vary from 10 to the power 5 to 10 to the power 9. Common mode gain, it will be 0, but practically around 10 to the power minus 5. Bandwidth is infinity, means ideally any type of frequency will work, but practically what will we see, it will attenuate and phases at high frequencies. When frequency is becoming very high, then there might be an attenuation of the signal. Now coming to the configurations of an op-amp. So we have first of all open loop configuration. Open loop configuration means there is no feedback from output to input. So this is a closed loop, but if you will observe in the open loop, I will show you the figure again. Now you can see there is no feedback from output to the input. There is no feedback from output to the input, so that is why it is a open loop configuration. Now in this case, what will we observe? The differential signal that is present between the inputs will be amplified. It will be amplified. It means V0 will be A times V1 minus V2. Why are we writing V1 minus V2? Because the convention is first you write the voltage given at non-inverting terminal, and that was V1, and then we write the one which is connected to the negative one, which is V2. So this is the formula. Therefore what is going to happen, because we are saying that the ideally the value of A is what, infinite, or it is very very high, so that means V out value will also be around infinity in this case. So it will reach to the positive or negative saturation very quickly. It depends on the values we are connecting then here, which is plus VCC and minus VCC. Now to control the gain, what we do, we use the closed loop configuration. As you can see in this diagram, there are two ways the connection can be made. If you see the first diagram, what is happening here is that we are having a feedback that goes to the non-inverting terminal, and if you see the second diagram, there is again a feedback, but that goes to the inverting terminal. So we have two types of feedback. If the output is connected to the positive, it is called as positive feedback. If the feedback is connected to the negative, it is a negative feedback. So positive feedback is having its own advantages, its own applications. Negative feedback is used for another set of applications. For example, if suppose we want to control the gain, if the aim is to control the gain, then we prefer using negative feedback. Suppose if our aim is to create oscillators, then we can use the positive feedback circuit for that purpose. So it depends on the type of application that we use. Then furthermore, once we discuss the negative feedback, we can have connections in two ways. We are having inverting configuration, we are having non-inverting configuration. The inverting and non-inverting configuration is based on where is input connected, where is input connected. So if you see diagram number 1, what is happening in diagram number 1? We have an input here. That input is connected to the inverting terminal. So it becomes inverting configuration. If you see second diagram, we are having input and input is connected to the non-inverting terminal. So it becomes non-inverting configuration. Now what will happen in inverting and non-inverting? We will observe it that the gain will be controlled. But before that, before we do analysis mathematically, there are some concepts which are important. First one, that if we talk about the op amps, we have a virtual short connection. Now how does that happen? As I said, the open loop configuration which has been shown here, the output can be calculated as A times V1 minus V2. So that means V1 minus V2 will be V0 upon A, and A value we are considering ideally infinite. So if you put A value infinity, what will happen? V1 minus V2 will be equal to V0 over infinity. So V1 minus V2 will be 0, because anything divided by infinity is 0. So that means what? V1 will be equal to V2. So it means the voltage V1 and the voltage V2, they are almost equal. So this is the concept of virtual short. Then we have a second approximation, that what if any one of the two voltages is grounded, means is 0. Suppose in this case, if suppose this was V1 and V2, so V2 is grounded, so it is 0. So by the concept of virtual short, this potential will also be 0. Okay, this particular potential shown in the red dot. Now the second concept is that because we are having infinite input impedance, because of that what will happen? The current will be 0. So ideally what we say, ideally there will be no current that enters inside the op amp. The current flowing into the input terminals is 0. But practically this is not possible, correct? Because if there is no current entering inside the op amp, then what is amplified then? So practically there is a very small current, as you have said, as you have read in the table also, that it is of the order of 10 to the power minus 5 to 10 to the power minus 12 kind of thing. So there will be a very small current, and it is because of that small current we get a very high amplification because of the multi-stage amplifiers being connected in the op amp. Now we are having the formulas here, that if we want to control the gain of the inverting op amp, what kind of relation we get in the inverting op amp. Now we can derive it also. You see what we have to do? We have to use two concepts. One is the concept of virtual short, or what we call as virtual ground, and second is the concept of no current inside op amp, right? So based on these two rules we can analyze the things. Now you see students, this is 0 volt, so by the concept of virtual short, this is also 0 volt. And second thing is that because of this input we are giving, suppose this is Vi, there will be some current here, let that current be I1. So after this point we have two paths, path 1, path 2. But will current pass through this path 2? The answer is no. Why? Because of the second rule, no current inside the op amp, means current cannot enter inside an op amp. So it has now only one path, which is upwards, so this is I1, means this current and this current is same, right? Let us call it as I2. So we can say I1 is equal to I2. Now we can use nodal analysis and we can convert I into V by R form. And in the nodal analysis we have read already in our previous videos. If this is R, this is V1 and V2, this is I, we can write this I as V1 minus V2 by R as per the direction of current. So in this way we can write here what is I1, Vi minus 0 by R1, and I2 can be written as, there are two nodes here and here, this current, this voltage is V0, 0 minus V0 by R2. So you can say Vi by R1 is equal to minus V0 over R2. So you can see we are getting this relation, that VO upon Vi is equal to minus of R2 by R1. So it is a very important relation that is actually telling you V out by V in is what? It is nothing but gain only, A. So this is nothing but gain. So it is telling you that the gain of this particular op amp is simply the ratio of two resistors. Now what will happen with this? You can control the gain. Suppose customer A will come, he needs a gain of 10. So what you can do, we can put suppose value of RF 100, R1 10, So we will give him gain of 10. Suppose customer 2 is coming, he wants the gain of 4 only. So we can keep maybe first one 100, second one 25 value. So we can get 4 as the gain value. So the point is we can control the gain as per the design requirement. In the same way, we are having a non-inverting op-amp, and you can analyze this also using the same two principles that I have discussed in the above one, right? So let us analyze. This is 0. So this is the Vi voltage given. So by the concept of virtual short, this is also Vi. So now we can write this current I1 and this current I2 will be same, because current cannot enter inside an op-amp. So we can write I1 is equal to I2. But what is I1 equal to? As per nodal analysis, 0 minus Vi upon I1. And what is I2? Vi minus V0 upon I2. Because this is one node, this is another node. Now, sorry, there is a one mistake, that we had to replace this with the R value. So this is R1 and this is R2. So you can see we got the relation. We can write V0 over R2 is equal to Vi 1 by R1 plus 1 by R2 by shifting the terms. So V0 by R2 is equal to Vi R1 plus R2 divided by R1 R2. So R2 will be cancelled with R2. So we get V0 by Vi is equal to R1 plus R2 by R1, which is equal to 1 plus R2 by R1. But R2 is nothing but, we are saying this is R1 and this is R2. So it is here RF written, so it will be 1 plus RF by R1. So in this formula, what are we concluding is that the gain is again same, because if the value of RF by R is very high, 1 can be ignored. So the value is RF by R, and last time we got minus RF by R. So both the values are almost same, and the negative sign that we got last time, this negative sign indicates simply that you are connecting your input to the inverting terminal. So the output will be out of phase, right? It will be 180 degree out of phase. That is what this minus is telling. Otherwise, this equation we are getting RF by R and the equation we are getting here, they are almost same. Then we have a special case of unity gain buffer, which is also called as a voltage follower. Now in the previous figure, if suppose we are having the value of RF as 0 and value of Ri as infinity, it will result in unity gain buffer. Now again, if we use the concept of virtual short, if this voltage is Vin, then the voltage here is also Vin, correct? So this Vin and this Vout, as you can see, it is the same line. So we can write Vout is equal to Vin, and if we take the ratio Vout by Vin, that value will come out as 1. So because the gain is 1, because Vout by Vin is A only, gain, so gain is 1, so it is called as a unity gain buffer. Unity gain means A value is 1. And why it's called voltage follower? Because output voltage is same as input. So output will be exactly whatever you are giving input. So it is a voltage follower. Then some quick quiz questions for you. Determine the output from the following circuit. So first thing, where is the input voltage connected? Input voltage is connected to the minus. So what will happen? Your output will be 180 degree out of phase with the input. So answer will be B. Determine the output voltage from the following circuit diagram. So students, where is the voltage given? The voltage right now is given to the minus, because this voltage V into is 0. Then it means that output will be out of phase. So obviously this diagram is not right. This option is not right. Second thing is that what is the gain value? Because if the value is inverted, that is fine, but how much is the amplification? Twice. So it means if the voltage here is 1 volt, it will be converted to 2 volt. So that is here. So it means option A is correct. Then what are the different applications of an op-amp where we can use it? There are a lot of applications, like we can use them to create adder circuits, subtractor circuits, differential amplifiers, then integrator, differentiator, which can be also used further for high pass filter and the low pass filter applications. Then comparison, if you want comparison of two signals, the comparator signal, then the filters also. So these are all wide range of applications where an op-amp can be used, And there are few more, like in the modern days, most of the sensors that we use with the Arduino and all, they are mostly made of the operational amplifiers. With this we complete all the topics which were part of unit 2, and with this we will like to end this video. I will see you in the next video, which will be regarding unit number 3. So till then, God bless you all and have a nice day. Thank you.